so now we're going to put our new ideas about parameterization into action, and we are going to parameterize a trajectory in a lot of different ways. So we have an object moving along the line segment from P, which is 1, 2, 4, to Q, which is negative 6, 8, 10. And we're going to parameterize the trajectory if the following are true. All right, before I even do any of that, I'm going to actually do a little bit of setup here. Okay, so we know that it's a line segment, and we know how line segments work. So we need our direction vector. So the direction vector is the vector from P to Q. So we take terminal minus initial. So we're going to take Q, which is negative 6, 8, 10. We're going to subtract. And I'm going to write pretty small because we have a lot to fit in this problem. So negative 6, 8, 10, take away 1, 2, 4. And that gets us a direction vector of negative 7, 6, 6. So that's our direction vector. And we know that our point, and we could use OP or OQ, either way. I always think of OP because then I go from P to Q. That's just how my brain works. So this would be 1, 2, 4. So then the basic line vector, L of t, is equal to negative 7, 6, 6, t plus 1, 2, 4. Or if you will, it's negative 7t plus 1, 6t plus 2, 6t plus 4. And let's just double check real quick. When t equals 0, if I put 0 in here, I would be at point P, right? Because if I put 0 in, that becomes 0 plus 1, 0 plus 2, 0 plus 4. So that would be point P, which is 1, 2, 4. I'm writing it as a vector, but I could write it as a point. It doesn't make any difference. There we go. So we're at that point. And if we're at t equals 1, that would be point Q. So it takes a time from 0 to 1, because if I put 1 in here, negative 7 plus 1 would be negative 6. 6 plus 2 would be 8. 6 plus 4 would be 10. So it takes 1 second, if you will, to do that. Okay. So our line works, and our line goes from 0 to 1 to get us through these points. It's not actually a restricted domain because this is a line piece. But I mean, if you want, you could say 0 to 1 to get to those 2 points. So I'm just going to tuck it in kind of over here for myself. Okay, so now let's look at the first one. So for the first one, we want to have a 2-second time interval and a constant speed. Well, a constant speed is no problem because if you look, right, that's my direction vector. So the speed would be the square root of 7 squared plus 6 squared plus 6 squared, say that 10 times fast, and that's a constant. Actually, we're going to need this later anyway, so let's just tuck in right here. We'll note the speed is the square root of 7 squared plus 6 squared plus 6 squared, which is the square root of 121, which is 11. That's a constant. Great. Okay, so I want to do this over a 2-second interval. So instead of going from 0 to 1, I want to go from 0 to 2. All right, well, constant speed 2-second interval means that we're going to use t divided by 2 in our parameterization. And this will work because I'm cutting the speed, if you will, the velocity in half when I do this. So that will make it so that this curve, L1 of t, is equal to, and so it's going to be negative 7, comma 6, comma 6 times t over 2, or if you like, plus 1, 2, 4. You can think of it, what you're doing is cutting each of these in half, right? So that would be negative 7 halves t plus 1, 6t, or 6 over 2 t, which we know is 3, so I'm just going to write 3t. 3t plus 2, and 6 over 2 is 3t plus 4. So I'm cutting my direction vector in half. Will this work? So let's check it. At t equals 0, when I put 0 in, I will have point 0 plus 1, which is 1, 0 plus 2, which is 2, and 0 plus 4, which is 4. And if t equals 2, right, because I want this to take 2 seconds, at t equals 2, I would be 7 over 2 times 2, which is negative 7, plus 1, which is negative 6. 3 times 2 is 6. 6 plus 2 is 8. And then 3 times 2 is 6. 6 plus 4 is 10. So I'm at point Q. So this works, right? So using this, right, cutting my parameter in half makes it take twice as long. It only took 1 second, but now it takes 2 seconds. But there's my parameterization. All right, so what about B? Well, B isn't really going to be any more difficult than this because we know how this should work. So if I want a constant speed over a 5-second interval, then I would use t divided by 5, right? So L2 of t would be, you take your negative 7, 6, 6 direction vector, you'd multiply it by t over 5 plus your 0.124, and that would get us negative 7 over 5t plus 1, 6 over 5t plus 2, and 6 over 5t plus 4. And we know that'll be from 0 to t to 5. 0 is less than or equal to t, which is less than or equal to 5. And we don't need to check it. We know this is going to work. I mean, you're welcome to check it if you want. It will. All right, so then what about the variable speed? Well, that's a bit trickier. Okay, so I want to vary my speed. And I want to make it e to the t. Now remember, the speed of the original is 11 because that's the square root of 7 squared plus 6 squared plus 6 squared. So if I want a speed of e to the t, I'm going to have to do a little bit of work here. So let's take letter C. Speed e to the t. Okay, so the original speed was, well, let's just do it this way. We're going to take our direction vector, negative 7, 6, 6. We're going to times it, or divide it, if you will, by 11, right, to make it a unit vector, if you will. And then you're going to multiply it by the new speed you want, which is e to the t. So this is going to be our direction vector now. So that would be negative 7 over 11 e to the t, 6 over 11 e to the t, 6 over 11 e to the t. This is now the direction vector we want. All right, so L3 of t is equal to that direction vector. So negative 7 e to the t over 11, 6 e to the t over 11, 6 e to the t over 11 times t plus 1, 2, 4. Right? It's not changing the fact that it's a line and it goes through that point. It's just changing how fast it does it. All right, so this would be negative 7, this is going to be weird, e to the t over 11t plus 1, 6 e to the t over 11t plus 2. Oh, let's see if I can fit it in here. 6 e to the t over 11 plus t plus 4. Ah, couldn't quite make it. 1 second. There, I rewrote it just so it fits in. And I'm not really going to worry about the domain on this. It's going to be really small. 0 actually still works. If you put 0 in here, e to the 0 is 1, and this become 0, and then it becomes 1, 2, 4. So 0 works, but the upper end is going to be strange because you need this piece to be equal to 1. So that would take some work. So we're not going to bother with that. Suffice to say, it moves in the same direction. All right, so how would I do it for a speed of 4t? Well, it's the same idea, right? We're just going to multiply, divide by 11, right? So if you want to see why that is, right, it's the speed, right? Maybe I should make a note, one sec. There, just to add that in. We're dividing by the speed of the original direction vector. Okay, so we want the speed on this one to be 4t. Okay, so you take your direction vector, you take negative 7, 6, 6, you divide it by 11, because you're dividing by the speed, and you multiply by 4t. And then that would get us, okay, negative 28, this one's going to be easier to write, negative 28 over 11 t, and then 6 over 11 t, or excuse me, 24, 6 times 4. So 24 over 11 t, and then 24 over 11 t, right? That would be our new direction vector, right? So this is new, I should say. It's in the same general, direction as the direction vector of old, but it's got a different pace to it. So those are new direction vectors. Okay, so then L4 of t would be equal to, you take negative 28 over 11 t, 24 over 11 t, 24 over 11 t, and then you multiply it by t, and you add the point, just like we always did, which will get us, oh, I'm going to have to erase that page number, I can feel it, so that I can write. So this is negative 28 over 11 t squared plus 1, 24 over 11 t squared plus 2, and then 24 over 11 t squared plus 4. There's our new vector. And just so you can all see them, I've put them all into Maple for us. Now, they're all right here. Now, I graphed them. Ooh, I should graph them with 5. One second. Okay, I changed it up. So I graphed the first one, which is the original one, with 0 to 1. Then L1 with 0 to 2, and L3 with 0 to 5. And you can see that those 3 graphs are going exactly where we wanted to. They're starting over here at P, and they're ending up here at Q. No problem. Actually, I'll say it's the cyan one is kind of messing us up a little bit. Let me take the cyan one out of there, because it doesn't look like it's starting at 1, 2, 4. So let me draw that one. There we go. And see, the pink one is too. I should have known. So just so you can get a sense of these two pictures. So it looks like, oh, it's not on the right scale, but notice it's telling us that that's 4 right there. See it? It's 1, 2, 4. It's changing the grid for us. So even though they don't look like they're correct, they are. So right now the blue one's dominating. So I don't have the transparency high enough on it that you can see it. But suffice to say, if there's anything sticking out of here, they would start showing up. So there's the pink one, which was the third one we did. And then let me add in the fourth one. There we go. So there's that. So they're all there. They're just kind of nested in this same line that's going from negative 1 to 4. And you can see, look, if you look at the axes, those aren't the 1 is in the right spot, but if you look at the other two, they say it's 2 and 4. They're actually starting at 1, 2, 4, just like we expect. So there's point P, there's point Q. They're all kind of there along that same path, but they're going about it at different rates. Some of them with constant speed, and some of them with a variable speed, right? Because, of course, we can't see the motion along this line segment as we do this. I can also say that I made the first 3 are pretty obvious what the t has to go from, but for these other 2, I know they have to be something, but I don't know what they are. So I can play around. They won't be a whole number, I can tell you that. They probably a decimal or a fraction or something. There you go. And if I just make it go to 2, that cyan one is shooting off that direction, right? So, and the pink one probably would be also. So it's just harder to see those. I did increase their transparency, so it makes it harder. But of course, if you wanted to look at each one of them individually, you could do that by getting rid of the colons, and there you have it, right? So it's doing the work. It's just a question of adjusting the t's for the two with variable speed to make it match.